You know, it's amazing when you think about it how these big scientific discoveries, they really do end up shaping the world around us. And today's deep dive is no different, right? It's all about the 2024 Nobel Prizes, which I know a lot of you have been asking about, especially in physics and chemistry.
And the exciting part is that both of these prizes are related to a technology that's almost as old as electronic computers themselves.
Oh, really?
Artificial neural networks.
ANNs.
Yeah.
I would have thought that was like a way more recent thing, not something that like goes all the way back to the beginning of computers.
It's a common misconception.
Yeah.
But the story of ANNs is full of twists and turns.
Oh,
They went from being this niche scientific model to something that is just absolutely everywhere in our lives now.
wow.
But to really appreciate that journey, we got to start with the physics prize.
All right, let's do it.
Because it's not just about a single discovery, it's about a fundamental shift in how we think about computation itself.
Ah.
When you really think about it, how do our brains actually learn and process information?
Right.
It's not like those step-by-step mathematical equations that we use in, like, traditional computers.
No, not at all.
And that's what John Hopfield and Jeffrey Hinton, the two recipients of this year's prize, were really struggling with back in the 1980s.
Okay.
They were really at the forefront of this idea that we could create a new approach to computation. And it was all inspired by the way our brains work.
So instead of trying to like force computers to think the way we do, it was more about like, let's look at how brains work and see if we can apply that to computers.
Exactly.
Yep.
Hopfield, back in 1982, he developed this model that wasn't just, a storage system for data.
Right.
It was a network where the behavior of all these interconnected units, they all work together to do the thinking, so to speak. Think of it like a network of magnets. Each magnet on its own may not be that impressive,
Right.
but when you have them all together, they create this like powerful magnetic field.
Yeah.
And that's kind of similar to how Hopfield's model worked.
It's amazing how something so like complex can come from these simpler interactions.
Absolutely.
It's kind of like, I don't know if this is the right analogy, but how individual neurons in our brains somehow create consciousness. You know what I mean?
Precisely. That's a great analogy.
It's wild.
And then Hinton, he comes along
Okay.
and takes things a step further with something called the Boltzmann machine.
The Boltzmann machine.
Yeah, it sounds complicated.
It does sound very complicated.
But it essentially uses a concept from physics,
Okay.
the Boltzmann distribution,
Okay.
to tackle even more complex learning tasks.
Okay, so give me an example. Like, how would that work in the real world?
Imagine you're trying to predict the weather.
Okay.
You can't be 100% certain,
Right?
right?
Of course.
But you can use probabilities based on past patterns.
Right.
That's what the Boltzmann distribution allows these artificial neural networks to do.
Oh, okay. So it's like, it's not just looking for an exact match. It's saying, okay, based on everything I know, this is the most likely scenario.
Exactly.
Interesting.
And so these early models were already showing that these artificial neural networks could learn and adapt in ways that traditional computers really struggled with.
That's really interesting.
But the real aha moment, the real breakthrough, came in 1986 with the development of something called backpropagation.
Backpropagation. Okay.
Yeah, it's a mouthful.
Yeah.
It was developed by Rumelhart, Hinton, again, and Williams. And this is where we see these multi-layered networks with hidden layers.
Hidden layers. So what are those?
Think of it like the behind-the-scenes work that goes into making a movie.
Oh.
You don't see everything that goes into making it, right?
Right.
But it's all essential
Versus there.
for the final product.
Yeah.
Hidden layers are kind of like that for ANNs.
Okay.
They allow this level of processing that just wasn't possible before.
Wow.
And it made them exponentially more powerful.
So it's like they unlocked a whole new level of complexity. Wow. Okay. Hidden layers. That's fascinating.
Yeah, it really is.
So they figured out how to make ANNs even more brain-like, basically.
You got it. They were on the right track, but of course there were still some challenges to overcome.
Yeah, hidden layers sounds super cool, but I'm guessing the story doesn't end there.
You're right, it doesn't.
What were some of the challenges they had to overcome?
Well, by the 2000s, ANNs were showing a lot of promise.
Okay.
But treating those really deep networks, the ones with tons of hidden layers,
Yeah.
that was still a major challenge.
Oh, how so?
Because think about it, right?
Okay.
The more layers you have,
Right.
the more complex those relationships between those neurons become.
Oh, okay.
And it becomes even harder to train that network effectively.
It's like adding more ingredients to a recipe.
Exactly.
You know,
Yeah,
it could be amazing, but you got to know how to balance all those flavors to make it work.
exactly. And so you need somebody who really understands those flavors. And that's where Jeffrey Hinton, once again, he steps in and just like changes the game.
This guy Hinton, he was on fire.
He was on a roll.
What did he do this time?
He comes up with this really clever idea of pre-training.
Free training. Okay, what is that?
So imagine, instead of just throwing the entire problem at the network all at once,
Right.
you first train it on a more fundamental level.
Okay, so like, what do you mean by that? Train it on a more fundamental level. Like, give me an example.
Okay, so think about teaching someone to recognize a cat in a photo,
Okay, yeah.
right? Like, you could just show them a bunch of cat photos and say, cat,
Cat.
cat, cat, cat. But what if instead
Yeah.
you first taught them to recognize, like, edges,
Right.
shapes, and then, like, footy textures?
Ah.
Okay.
So it's like giving the network a basic understanding of the building blocks
Exactly.
before you ask it to just like figure out this complex image.
Exactly. And that's precisely what Hinton did with these things called restrictor Boltzmann machines, or RBMs.
RBMs.
Yeah, it's a mouthful, but just remember, RBMs, they were that pre-training stage.
Yeah.
They were finding those patterns in the data before we even knew what the ultimate task would be.
Wow, that is such a smart approach.
It really is.
Because if you think about it, like it's like,
Yeah. Yeah.
laying the foundation and
Yeah.
building this really strong structure before you even start like adding the walls and the roof and all the fancy stuff.
You got it.
Yeah.
And that brings us to the Nobel Prize in chemistry,
Oh, okay.
which went to the development of something called AlphaFold.
AlphaFold. No,
Well,
remind me what that is again.
AlphaFold used these very same principles
Okay.
to solve one of the biggest puzzles in biology,
Okay.
protein folding.
Protein folding. Right.
Because proteins are like the workhorses of our cells.
They do all the things.
They do everything.
Yeah.
They transport molecules, they catalyze reactions.
Right.
And their function is completely tied to their 3D shape.
Right.
But determining that shape from their amino acid sequence,
Yeah.
that is incredibly complex.
How complex are we talking? Like, paint me a picture.
Imagine a piece of paper.
Okay. Got it.
Now imagine folding that piece of paper in every single way possible.
That's a lot of ways to fold a piece of paper.
That's a lot, right?
It is.
Now imagine a protein, which is like that piece of paper, but instead of just being a flat sheet,
Uh-huh.
it's this long chain of hundreds or even thousands of amino acids all linked together.
Okay.
The number of ways that thing can fold is astronomical.
Wow.
It's more than the number of atoms in the universe.
No way.
Yes.
So how on earth are scientists supposed to figure out the correct shape? Like, how do they even begin to tackle that?
Well, for a long time, it was this incredibly slow and resource-intensive process.
Yeah, that.
But AlphaFold changed everything.
Okay.
And it did it by using the power of deep learning
Okay.
and those pre-training principles we were just talking about.
Ah, this is where it all comes together.
It all connects.
Okay, so how did AlphaFold use those things to tackle protein folding? So AlphaFold used pre-training and deep learning
Right.
to figure out protein folding. But how? Like, did it have this huge database of like every possible protein shape or what?
It's actually even cooler than that.
Okay, how so?
AlphaFold, it doesn't just rely on brute force memorization.
Okay.
Remember those contact maps we talked about earlier?
Yeah, like the connect the dots for proteins.
Exactly. The original AlphaFold, it used those
Okay.
to predict which parts of the amino acid chain
Right.
would be close together in the final folded structure.
Okay.
But then came AlphaFold 2,
Okay.
and that just took things to a whole new level.
AlphaFold 2, the sequel.
The sequel.
Always better than the original.
Exactly.
Okay, so what made it so special?
AlphaFold 2, it moved beyond just predicting contacts.
Okay.
It was actually learning the underlying physics
Wow.
of how proteins fold.
So it wasn't just matching patterns, it was like figuring out the rules of the game.
Precisely.
Wow.
And it's like
Yeah.
the difference between just memorizing your multiplication tables
Right.
versus actually understanding the concept of multiplication.
Oh, okay.
Right.
So it really understood what it was doing.
It really did. And
Yeah.
the impact was huge.
Yeah.
Scientists could spend years
Right.
and tons of resources
Yeah.
trying to figure out the structure of just one protein.
Right.
And now suddenly AlphaFold can predict it, often with incredible accuracy, in sometimes minutes.
That's insane. Okay, that's a game changer for sure.
Huge game changer.
For scientific research.
Absolutely.
But it feels like it goes even beyond that.
Oh, yeah.
I feel like I've heard about ANNs being used for so many different things now.
Oh,
It's
absolutely.
not just this, like, niche thing anymore.
No, it's exploding.
Yeah.
And the most amazing things is that the team at DeepMind,
Okay.
they made AlphaFold's code public.
Really?
Yeah, they just made it available for anyone to use,
Wow.
which is like giving every scientist in the world a superpowered microscope.
That is incredible. Talk about democratizing access to knowledge.
Exactly.
Wow.
That's just one example. We've gone from physics equations to protein folding,
Right.
all thanks to ANNs.
It's wild.
It really is.
Like, it's already doing so much.
Oh, and that's just the tip of the iceberg.
What?
Because this technology isn't stuck in some lab somewhere.
Right.
It's everywhere in our lives right now.
No way, really.
Think about it. Every time you unlock your phone
Yeah.
using facial recognition,
Yeah.
ANN,
Shut up. Really?
Yeah.
I never even thought about that. I just thought it was magic.
it's not magic, it's artificial neural networks.
That's so cool.
It is really cool. And when your inbox filters out spam,
Okay.
thank an ANN for a cleaner inbox.
Okay, you know what? I actually do appreciate that because spam emails are the worst.
The worst.
So thank you, ANNs, for that.
You got it. And all those personalized recommendations you get
Yes.
on like streaming services and shopping websites.
Yes, how do they know?
ANNs.
ANNs. It's all powered by ANNs.
It really is incredible.
It really is. It's like they're the little helpers behind the scenes making our digital lives possible.
They really are.
It's like a whole army of little digital helpers powered by ANNs. That is so cool.
It really is.
So we've covered a lot of ground today.
We have.
From the birth of ANNs, going all the way back to the 1940s.
That's the beginning.
With those early models, and now they're predicting protein structures, filtering our spam, recommending us movies. It's amazing.
It's only going to get more amazing from here, too.
Well, I can't even imagine.
And that's the thing, the future of artificial neural networks.
Yeah.
It's brimming with these incredible possibilities.
It really is. It's exciting. It's a little bit scary,
A little bit.
but it's mostly exciting.
Mostly exciting.
Yeah, who knows what they're going to come up with next. Well, that's about all the time we have for today's deep dive.
Sounds good.
But before we go, we want to leave you with a thought, something to ponder.
Always.
If artificial neural networks can already do all of this,
Right.
what else might they be capable of in the future?
The possibilities are endless.
Exactly. Until next time, keep exploring, keep learning, and keep diving